G'day there. Just want to welcome you to the exciting new world of simple harmonic motion, where things move back and forth along fixed paths with a constant period. Maximum speed in the center, zero speed at the edges, and the acceleration, zero in the center, maximum at the edges. Righto, level 3 physics. We're out here this morning to have a little chat about S.H.M. That stands for simple harmonic motion. We're talking about simple harmonic motion. We're thinking about a body in motion that follows a repeated path back and forth over and over again. The sort of thing you might see inside a grandfather clock as the pendulum swings back and forth, or one of those baby toys, a funny little thing on a spring that bounces up and down, following a fixed path over and over and over again. And so, to introduce this new type of motion, we're going to start by chatting about a pendulum, and I want you to think about a pendulum as it swings back and forth. We've got the extreme points, A and C, which we call the amplitude points, and then B we call the equilibrium point. The equilibrium point is where the pendulum would hang if it weren't in motion. Now what I want you to do is to consider what do we know about the three important quantities of motion: displacement, velocity, and acceleration at each of those points, A, B, and C. Just repeat that again. What do we know about displacement? Displacement being how far is that pendulum bob from its equilibrium position. Velocity being how fast is that pendulum bob moving. And acceleration being how great is the acceleration of the pendulum bob. And each time thinking about those as a vector quantity, so giving them a size and a direction at A, B, and C. Maybe have a go at writing that down if you can. Let's start by talking about displacement, shall we? The displacement y at point A is a negative maximum. Negative because it's moved left from the equilibrium position, and left is negative, right is positive. And so point C is going to be a positive maximum. Position B is 0. The speed at each of those points, well, hopefully you know from your playground experiences that at point A and C you momentarily stop, whilst at point B you're really rushing along, either back or forth, back or forth. And so that's a positive or a negative maximum at position B. And finally, the acceleration. Thinking about position B first, if the swing, or the pendulum, is just at position B, it doesn't tend to move. And that lets us know that its acceleration must be 0. At position A, we know that it's getting slower and slower and slower as it approaches A, and then after it leaves A, it gets faster and faster and faster, back towards the equilibrium position. So that means that at position A, the acceleration is directed to the right. That makes it a positive acceleration. And the opposite argument can apply at position C. It gets slower and slower as it approaches C, and then after it's been at C, it accelerates back towards the equilibrium position. So that acceleration is negative to the left. Now the other thing that we can consider is the size of that acceleration. Now if you pull back a swing just a little bit and let it go, it tends to accelerate gently and just gently swing back and forth, low acceleration. However, if you really pull that swing back and let it go, it has a much greater acceleration. So that's teaching us that the size of the acceleration depends on the size of the displacement. And that brings us to a critical, key, fundamental, underlying, eternal truth about all simple harmonic motion. And that is that the acceleration depends on the size of the displacement and is in the opposite direction to the displacement. Let's write that down. We write it down like that. A equals minus ky. A is the acceleration of the body. Minus is telling us that there's an opposite direction in there. Opposite to which direction? The y, the displacement. So the acceleration and the displacement are always in opposite directions. If you pull the swing back to the left, it tends to go to the right when you let it go. And if you push it to the right, don't try this at home, then let it go, it swings back and smacks into your knees. K is just some number, and we're going to find out more about K later on. But at the moment, it's just a constant. It's just some number to do with our system. So, key fundamentals of simple harmonic motion is that the acceleration depends on the displacement. It's proportional to the size of the displacement, but opposite in direction to the displacement. It would be a good idea to get that tattooed onto you somewhere.